Hey everybody, welcome to our next lecture. Today we're going to talk a little bit about acid-base theory and then acid-base neutralization reactions. So the first thing is, let's actually talk about the neutralization reaction first. So a neutralization reaction is really the same thing as a double replacement reaction. The difference is it's between an acid and a base. So if I take an acid like HCl and I react HCl with a base, so this is my acid. And in chemistry, acids are typically things that have hydrogen out front, like HCl, which is the acid in your stomach. So if I take an acid and react it with a base, and a base typically has something that has the hydroxide ion in it. So let's say I use something like sodium hydroxide, NaOH. So we know how to recognize an acid. It's got the hydrogen in front, and the base has the hydroxide at the end. So this is a double replacement reaction. So what happens is the hydrogen will come over here and grab the hydroxide, and the sodium will grab the chlorine. Because acids and bases react together to neutralize, which is why they're called neutralization reactions. So if hydrogen grabs the hydroxide, I form this dangerous compound known as hydrogen hydroxide, which is, if we rewrite this, what's HOH? It's just water. And water is neutral. Water has a pH of 7. What's left? NaCl plus sodium chloride. So, which is also a neutral compound. It doesn't affect the pH of a solution at all. So it's a double replacement reaction, but it's also a neutralization as well. I produce a neutral substance, water, and I produce another neutral substance, sodium chloride. So to talk a little bit about, by the way, this is it. This is the entire acid-base neutralization theory. We take an acid plus a base, and we react them to form two things: water, H2O, or hydrogen hydroxide, if you like that better, H2O plus a salt. Now, in chemistry, a salt is anything that has a metal ion and a nonmetal ion. All right, so basically any ionic compound is a salt. This is the basis behind all acid-base neutralization reactions. So let's go into a little bit more detail about acids and bases in terms of pH. So if we're talking about acids and bases, we're talking about the metric which we kind of analyze these by, and that is by pH. And acids typically have low pHs, and bases have, yeah, right, I was about to write the word base again. Bases have high pHs. In terms of a pH scale, we go from around 0 up to around 14. And right smack in the middle is 7, and this is what we define as neutral, a neutral pH. So anything below 7 is going to be acidic. Anything above 7, and I mean anything above 7, is going to be basic. And it runs the whole gamut of things that we come in contact all the time. If we want to talk about soap, we might have a pH right around up in here. A bleach might have a little bit higher pH. Drain cleaner might be a POH. Like if I had KOH, potassium hydroxide drain cleaner, it might have a pH of 14. Blood is going to be right about here. Blood has a pH of about 7.4. Coffee is down here, a pH about 5.5, as does most beverages. Coffee, soda, I can't talk about the other beverages. Lemon juice is going to be down here. Lemon juice is going to have a pH around 2. So this runs the gamut of the pH scale. And pH scale, or if you take AP chemistry, we'll get into kind of talking about what the pH scale is. So suffice it to say that in an acid-base neutralization reaction, we take something with a low pH, something with a high pH, we react it together to make water, which has pH 7, plus some type of salt, which is also pH 7, all right? So if you have what we call heartburn, your stomach is producing excess acid that is working your way up esophagus. So if you have acid and you want to neutralize it, you have to take a base. So you can take some Tums or Rolaids or some kind of base to help neutralize the acid. That's what acid indigestion is. It's just you have excess acid produced in your stomach. If you end up most baking, most recipes require that the product to be neutral. So if you have an acid, you have to neutralize it with a base. So if you added something like lemon juice to a cake, I don't know what kind of cake you do that, but if you add lemon juice, you probably have to add something like baking soda. Baking soda is a base, all right? So it's pretty interesting. But let's get back to acid and base theory. So there's really two theories for describing what makes an acid and a base and a base. They don't always work. The theory we're going to talk about right now is which is known as Arrhenius theory. Is It works okay for the stereotypical acids and bases, and it says this. It says that an acid is something that is going to put hydrogen ions into solution. Okay. So if you imagine I take something like HCl, whoops, hold on, let me read that again, HCl, and I know that HCl starts off as a gas, and if you bubbled hydrochloric acid into water, it would dissociate and actually form H plus ions that are aqueous, as well as Cl minus ions, which are aqueous. Okay? So an acid is really something that adds H plus ions to solution. So we would expect acidic solutions to have lots of H plus ions roaming around. So if you put a piece of zinc in with hydrochloric acid, if I wrote, I'm going to write a molecular equation and then write a net ionic equation. I'll put a piece of zinc in, that's a terrible Z, but zinc plus HCl goes to form what happens is the hydrogen ion will react with the zinc and will force the zinc to take electrons. So it'll end up forming, the hydrogen ion is going to, it's the other way around. The zinc is going to force the hydrogen ion to take electrons. So it's going to end up forming zinc chloride, ZnCl2 plus H2 as a gas. And then to balance this, I just need a 2 here. So if I wrote this out as a net ionic equations, solids like zinc are left alone. Zinc plus 2H plus aqueous plus 2 Cl minus aqueous go to produce, where are we? Zn plus 2 aqueous, because zinc chloride is soluble, plus 2 Cl aqueous plus H2. Oops, and H2 is a gas. So if I choose a different pen here, the spectator ions become chlorine and chlorine, and that's it. Everything else is included. So the net ionic equation becomes zinc plus 2H plus goes to form zinc plus 2 plus H2 as a gas is your net ionic equation. Okay, so Arrhenius theory says an acid is something that adds hydrogen ions into solution. And a base, if we comparatively look at what a base does, Arrhenius theory says a base is going to add hydroxide, OH negative or hydroxide ions into solution. And that's great because we know lots of bases. You can go to Home Depot and buy something called NaOH or KOH, and these are great bases. We use these for drain cleaner or even an oven cleaner. It's just about right, drain oven, drain cleaner. And the problem is this, is that not every base that you come across has hydroxide. And if you ever picked up a can of bleach, you know it's a base. But the problem is this. Okay, the problem with the Arrhenius theory is it does not count for why bleach is a base. The active ingredient in bleach, the thing that makes it slippery, the thing that kills bacteria and all sorts of things, is this stuff called sodium hypochlorite. And if you notice, it doesn't have any OH. So Arrhenius theory has a problem when discussing things like sodium hypochlorite, right? So there's a competing theory for what what bases are. So the second theory for base. So the second theory is what's called Bronsted-Lowry theory. Let me pause while I write that down. Okay, so Bronsted-Lowry theory is this competing theory for what acids and bases are. And a Bronsted-Lowry theory says this about acids. It says acids can be thought of as proton donors. All right, now before we start getting confused, like where the heck is a proton coming from? Go back to Arrhenius theory and ask yourself, what does an acid do? An acid from Arrhenius theory puts H plus ions into solution. Well, what does H plus, and by the way, it should be H plus 1, what does H plus 1 actually mean? How many, if I were to analyze hydrogen, it has 1 proton and it has 1 electron and 0 neutrons. If hydrogen becomes H plus 1, it means it is kicking out this electron. So what's left? H plus 1 is really just a proton, all right? So Bronsted-Lowry theory says acids are things that can donate protons, all right? Things that can donate protons. And in Bronsted-Lowry theory, believe it or not, water can act as a proton donor. And I can't spell the word proton. There's an R. Water can act as a proton donor. Why? Because water has a hydrogen ion, a proton, that it can donate to something else. Okay. Well, if an acid is a proton donor, then what is a base? A base is what's known as a proton acceptor. So a base is a proton acceptor. Bases are things that can take protons, right? So if you want to take a substance that can take protons, imagine a substance like NH3. NH3 is ammonia. And if you put ammonia into water, this NH3 is a base can accept a proton. And if it does, if it takes a proton, it will end up forming NH4 plus 1. So NH3 has a spot that can take a proton, and if it does, it is a base. And if it accepts a proton, here it is, it grabs this extra proton, NH4, and the extra proton, it just has a plus 1 charge by itself. Okay, so let's put Bronsted-Lowry theory into action. All right, let's kind of show how we can use Bronsted-Lowry to prove why acids are acids and bases are bases. So I want to talk about Bronsted-Lowry theory, imagining it in this particular case. So this is HCN. This is what we know is to be a weak acid. There's a bunch of weak acids that are out there. Baking soda is a weak base. Acetic acid, citric acid, ascorbic acid, those are all weak acids. So I take a weak acid plus water, what's going to happen? Well, it's important to note that HCN is going to act like my acid. And what do acids do? They donate protons, right? So at some point, that's an A, my acid, HCN, has to donate a proton. Well, where's the proton? Which one of these three things in here is going to be the proton? Yep, it's got to be the H, right? So if H is going to donate a proton, who's it going to donate it to? It's got to be the other species in here. Okay, so this is where it gets a little bit strange. The acid is going to donate a proton to this. So if this is the case, and this is where it gets a little strange, then water in this particular compound, in this particular reaction has to act as my base. Okay, so if water is going to act like a base, it is going to accept a proton, all right? So a proton is basically going to go from here to here. So what's going to happen? Well, I'm going to make, when the acid donates a proton, what's left is just going to be Cn minus, right, plus water with an additional proton, H3O plus. Okay, so what we see over here, this thing right here, which is you've probably never seen before, H3O plus, is what's known as the hydronium ion. Let me write that down. So a hydronium ion, H3O plus, is just water with an extra proton attached. So this is where Bronsted-Lowry theory kind of shows up with Arrhenius theory. Arrhenius theory said acids put hydrogen ions in solution, Bronsted-Lowry theory says acids put hydronium ions into solution. So this hydronium ion is just like the H plus we get from Arrhenius theory, okay? Just so we can kind of compare. So this is it. Okay, I have an acid which has donated a proton to a base. Let's try this again with another problem. Let's look at something like NH3, and we saw this one before, but let's work with this again. NH3 plus H2O. Now, in this case, NH3 is definitely a base. So it is definitely a thing that is going to accept a proton. Well, if you put NH3 into water, where are the protons going to come from? Yep, they got to come from right here. So in this particular problem, water, it isn't acting like a base anymore. Water, because it has protons, is going to act like the acid. So water is going to donate a proton. So a proton is going to come off of water and go over to NH3. So let's see what happens. If the proton comes off of water and goes over here, I have to end up making NH4 plus 1, all right, plus what's left over after water gets rid of a proton, a hydroxide ion, OH minus. All right, great. Now, take a minute and let's look at both of these. So we said that bases are things that put hydroxide ions in solution and will give us a high pH. We'll take a look. When you put ammonia into water, guess what it makes? It makes lots of hydroxides. It's going to make the pH go up when you put ammonia into water. Acids put hydrogen ions, or in the case of Bronsted-Lowry theory, hydronium ions into solution. The moment I put HCN into water, it's going to make H3O+, which is the same as H+, which is going to make the pH go down. Okay, so this is just kind of a quick little thing on how Bronsted-Lowry theory works. All right, so the next question would be, we need to kind of analyze this a little bit more because there's more going on here. Let's take a look at Bronsted-Lowry theory for our active ingredient in bleach, sodium hypochlorite. Now, I should say that this is an ionic compound and it is soluble in water. So when sodium hypochlorite goes into water, it ends up forming two things. Sodium ions, which are going to turn out to be our spectators, and we just kind of completely eliminate, plus OCl negative ions. Okay, so imagine this. I'm going to take OCl, which is aqueous, and I'm going to write OCl. Imagine taking OCl and putting it into water. OCl negative, aqueous, plus H2O. So which one of these is going to be my acid? Which one of these is going to be the base? Well, we already know that sodium hypochlorite, the active ingredient in bleach is a base. So if that's the case, then I know that this has got to be my base. It has to be the proton acceptor. If this is going to accept protons, I mean, look at it. It's missing something out here. It's a negative charge. Wouldn't it be nice if it took a proton? Okay, that means the water has to act like my acid, which means it is going to donate a proton. And I can't spell donate. Anyways, there it is. So the water is going to donate a proton over to here. So I'm going to end up forming, wait for it, HOCl, which is neutral, plus what's left over after the H comes off of water? OH negative. Look at that. And it's the hydroxide which makes the pH shoot up. It's this hydroxide ion which is produced from sodium hypochlorite that makes the pH of bleach really high, which means bleach is a base. And this is what explains it, all right? So we can use Bronsted-Lowry theory to explain why bleach is a base. We cannot use Arrhenius theory to explain why sodium hypochlorite is a base, okay? All right, good. Now, all right, there's more to the story as always. So let's figure out this reaction real quick. So we use this as an example. HF, it already has H in front of it, so we know this has got to act as my acid, and therefore the water in this problem has to act as my base. So acids are going to donate protons, the hydrogen's going to come off of here and go over to water. So I'm going to end up forming H3O plus F minus. So we're pretty sure that HF and the H2O act as the acid and the base respectively. But there's something else that happens. Now, if you imagine kind of putting up a brick wall and you don't actually see what's going over on this side, now I end up with something H3O plus and F minus. There's something new going on. So if you could imagine right now, imagine I'm going to put a box over this entire side and not let you see anything that's over here. And all you see instead are these two products. What would you say? What would I say if I gave you a lot of H3O plus and F minus? Well, you'd probably say, if these are the only things I gave you, you would probably say that H3O plus looks like it's kind of like an acid because it's got an extra proton, and F minus could act like a base because it looks like it has a space where it could accept the protons. So in Bronsted-Lowry theory, we have things where we have an extra acid and an extra base which is produced during the process of the original reaction. So I'm going to put a word over here and we'll kind of talk about what this word means. So when we look at the H3O plus, the hydronium ion and the fluorine ion, they look like this could act as an acid and this could act as a base. In fact, there's a direct relationship between the things we started with and the things that are produced. The HF starts off as my acid. And when the HF is ionized and the hydrogen comes off of it, the HF donates a proton, it goes to make, let me rewrite this a little bit differently. So I wrote this a little bit differently. HF starts out acting like my acid. But when HF is done, after it's donated the proton, it forms something which is F minus. And F minus, as we got done saying, kind of looks like it could be a base. So what I want you to think about is when HF does its thing, when HF donates a proton, it creates a base which is related. So I'm going to put the word related up here, except I'm writing retake, and I don't know why I wrote that. So when HF donates a proton, it forms F minus. It forms a base which is related or coupled with the acid. And on the other side, water in this problem acts like a base. When water accepts a proton, it ends up forming something that looks like it could act as an acid. So when water accepts a proton, it forms an acid which is also coupled, right? This process of this base is coupled with this acid, is coupled or related to the, I forgot coupled to the base. So Bronsted-Lowry theory has the products are coupled or related to the things that came before. And what they call these things in Bronsted-Lowry theory, what we call the products of these reactions are the conjugates. And this is a fancy word, conjugate. So if I start off with an acid, the base that I end up with is what's known as the conjugate base. And if you do a Google search right now for the word conjugate, you're going to come up with three things in the definition. You're going to come up with coupled, related, and there's one more. Let me go look at it. Conjugate means coupled, related, or connected. So if I start with an acid, I'm going to have related to it or connected to it what's known as a conjugate. I'm going to write the new term in here, conjugate, I'll abbreviate it, conjugate base. So an acid always has a conjugate base which is coupled to it. A base is going to have a conjugate acid which is coupled to it. So whenever people hear the word conjugate, and I think back to my time when I first heard the word conjugate, I had no idea what it meant until I looked up the dictionary definitions for conjugate, coupled, related, or connected. An acid, which is a proton donor, makes a base which is coupled with it, what we know as a conjugate base. A base ends up making an acid which is coupled or related to it called a conjugate acid. So let's go through another problem and kind of talk about where the conjugate acids and bases are. All right, let's take a look at a new problem. This is acetic acid, HC2H3O2, plus water. So I want to be able to predict what the products are. I want to be able to identify. So if I want to answer if I want to answer this problem, I want to be able to identify the acid and the base plus the conjugate acid plus base. Okay? So which of these two things, water or acetic acid, is going to act like the acid in the problem? You could probably figure out that the acetic acid is going to act like my acid. And if this is the acid, then the water has to be the base. All right? So what's going to happen? Acetic acid is going to donate a proton. This proton is going to get donated to water, and it's going to go produce H3O plus. And what else? As this donates a proton, the acetate ion, C2H3O2, is going to be left over. C2H3O2 negative is left over. So the acid donates a proton, the base accepts a proton. Now, what we want to be able to figure out is what are the conjugate acids and conjugate base. The thing to remember is that an acid will always make a conjugate base. And a base will always end up making a conjugate acid, right? So let's do the base first. What does the base make? The base ends up making, by accepting a proton, has to make a conjugate acid. So here it is. H3O plus is something that, given the chance, H3O plus has an extra proton and could donate it. So H3O plus is going to be my conjugate acid for the problem. And I can't spell the word acid, but there we go. So it's H3O plus is a conjugate acid. The acetate ion, or C2H3O2, has to be my conjugate base. So ask yourself, why? Why does this thing have to act like a base? Bases are things that go and accept protons. Does this thing have any spot on here where it could possibly accept a proton? And you could probably say, well, yeah, if it grabs a proton back, it could act just like the acid that it started with, right? So let me do one more example. I'm going to pick a different problem, and you're going to tell me what the acid, base, conjugate acid, and conjugate base are, all right? Okay, so here's a hypothetical problem. Imagine I start with a carbonate ion, and I add the carbonate ion, react it with water, and end up producing HCO3 negative plus OH. This is -1, and OH -1, all right? So which of these two species in the original problem is the acid? Which one is the thing that donates the proton? Now, if you're confused, make sure you understand what donating a proton does. What will water look like at the end if water donates a proton? Can the carbonate ion donate a proton? Does it have any hydrogens? So if you ask yourself, does it have hydrogen, question mark? If it has no, then this can't be your acid. It has to be the base, all right? So this is the only thing in the reactants that has a hydrogen. So this is hydrogen, yes. So it has to be the acid. Okay, so we know what our acid and we know what our base are. So question time. Both of the species over here at the end have negatives. Does that mean that they're both going to be acids or bases? Okay, so test yourself. Which one of these two things at the very end could act like something that could donate a proton? So you got two choices. Either got this one or you got this one. Which one of these two things can donate a proton? Now, is it likely that OH is going to donate this proton here to become O? Well, that's out of the question. If that's the case, then OH has to act like a base because it's only got a spot right here to accept another proton. So OH negative has to be the conjugate base, which is produced by the acid. Acids produce conjugate bases, which means the base has to produce a conjugate acid, right? Base produces conjugate acid. HCO3 has a hydrogen which it could possibly donate. Okay, so we're about 30 minutes in. That's all we're doing for this particular lecture. I have a couple pages in the book for you to read. The book you're reading, page 740 and 741, and that's it. This is about Bronsted-Lowry theory. Acid-base neutralizations are really pretty simple. I did throw a couple homework problems on. So there are homework problems on Chem 101, and there will also be a new Google quiz for you to take. And I believe the new Google quiz is due Wednesday. Okay? All right. Have a great day, everybody.